Imagine it is 2:47 in the morning. The application is slow. The dashboard is red. Open transactions are climbing. A checkout request is stuck behind a lock. Someone says the word deadlock, and suddenly the room gets quiet. This is where databases stop being a feature list and become a survival system. The question is no longer which database has the best logo, the trendiest cloud service, or the loudest marketing campaign. The question is simple: if the database fails, what survives? Are committed transactions still true? Are failed transactions cleanly erased? Can the system replay its log and come back without mystery data loss? This video is about why PostgreSQL became the answer engineers trust when being wrong is expensive. Most databases are fine on normal days. Normal days are easy. The real test is the bad day. Partial writes. Concurrent updates. Application bugs. Disk stalls. Replicas behind. A CTO asking whether the numbers on screen can still be trusted. That is the real issue. Correctness under pressure. A committed transaction must be real. A failed one must disappear. Readers and writers need predictable behavior when traffic is ugly. And after a crash, recovery must land on a known consistent state. PostgreSQL earned trust because it kept these promises again and again. Not in demos. In incident rooms. In logs. In recoveries where the system came back, the rollback was clean, and the team could move on. Here is the roadmap. First, we go back to Berkeley and the research culture that shaped PostgreSQL before it was popular. Then we look at the trust mechanics: ACID, MVCC, write-ahead logging, crash recovery, and clean rollback. After that, we look at the extension mode. PostGIS for geospatial. Timescale DB for time series. C2s for distribution. Godot for compliance. Foreign data wrappers. And eventually vector. Then we follow the cloud era, where every major platform chose PostgreSQL as a flagship relational service. Finally, we look at the AI era, where vector turned PostgreSQL from a boring relational database into a serious platform for RAG applications. The point is not that PostgreSQL won overnight. The point is that every era gave it one more reason to matter. Trust in a database is not built in a product launch. It is built across thousands of production incidents. The first decision was ACID correctness. Not as a marketing claim. As a design constraint. When PostgreSQL says a transaction committed, it committed. When it says it failed, nothing half persisted. This was not universal in the 2000s. The second was MVCC. Multi-version concurrency control. Readers and writers do not block each other. Transaction T1 reads the orders table while transaction T2 updates it. They see different snapshots. Both consistent. Zero locks. This is why PostgreSQL performance stays predictable under mixed workloads. The third was write-ahead logging. Every change goes to the WAL before it touches data files. The log on screen is a real PostgreSQL 18 recovery sequence with actual LSN numbers. Power was cut. The server restarted. WAL replayed. Recovery complete. Zero data lost. These three decisions were made because correctness was the design principle, not because they were easy. Rather than becoming a specialized database for every emerging workload, PostgreSQL became a platform that let extensions bring those workloads to it. PostGIS turned PostgreSQL into a world-class spatial database. GIS engineers who had been paying Oracle spatial licenses suddenly had a fully capable open-source alternative inside a database they already knew. Timescale DB brought time series. IoT sensor data, application metrics, infrastructure observability. Same SQL, same transaction guarantees. Hypertable storage underneath. The vector changed the AI story. Instead of a separate vector store, teams could store embeddings inside the same PostgreSQL that held their transactional data. One query could combine semantic search with SQL filters. One consistency model. CETAs brought horizontal sharding. Distributed PostgreSQL without rewriting queries. PostgreSQL did not need to become every database. It needed to be stable enough that other engineering teams could bring their specialized workloads to it. That architectural humility became the moat. Every major cloud provider chose PostgreSQL as their flagship relational offering, and that decision accelerated the entire ecosystem. AWS built RDS PostgreSQL and Aurora PostgreSQL. Google Cloud built AlloyDB with columnar caching. Azure built Flexible Server with built-in PG Bouncer. Every serious cloud provider now offers managed PostgreSQL. But the more interesting story is the new generation. Neon built serverless PostgreSQL with instant database branching. Fork a production database in milliseconds. Supabase built a full developer platform and became a credible Firebase alternative. EDB and Crunchy Data serve enterprises that need hardened, supported deployments. Cloud brought features that were previously manual into the standard offering. Read replicas. Point-in-time recovery. Automatic failover. These made PostgreSQL viable for teams without dedicated DBAs. And critically, the open protocol means no vendor lock-in. Write SQL against Neon today. Move to AWS RDS tomorrow. Run on-premises next year. The queries work everywhere. The AI wave created a new database requirement most teams had not planned for. Applications needed to store and query vector embeddings. The first wave of AI tooling pointed teams towards specialized vector databases. A separate system for vectors alongside your existing transactional database. 2 databases, 2 consistency models, 2 failure modes. Then vectors shipped and the calculus changed. A single query could combine cosine similarity search with SQL where filters. Find documents similar to this embedding, published in the last 30 days, belonging to this tenant. One database. One transaction. No sync lag. The vector SQL on screen is real. Select Content and Similarity Score from Documents or Tenant and Date filters, order by vector distance, limit 5. This query cannot exist if your vector store and relational store are separate systems. For most RAG applications, PostgreSQL with vector is sufficient. Vector supports IVF flat and HNSW indexing for approximate nearest neighbor search at production scale. PostgreSQL did not win by outmarketing Oracle or outscaling MySQL. It won by being boring in the right places. By implementing ACID correctly when others skipped it. By building WAL when it would have been easier not to. By staying open source when acquisition offers must have been tempting. And powerful where it matters. Extensible enough for PostGIS. Open enough for vector. Stable enough for banks. Portable enough for cloud infrastructure. Correct enough for systems where the cost of being wrong is measured in real money. In 2026, PostgreSQL 18 ships with 3x I/O gains. PostgreSQL 19 enters feature freeze. Every AI application being built today is deciding where to store vectors. PostgreSQL is in that conversation in a way impossible to predict from a Berkeley lab in 1986. If this was useful, subscribe to Dr. Ibrar Ahmed's channel. The next deep dive goes further.